Today we are going to look at the topic of inequalities discussed in the MAT 1510, XAT 1510 module, and this is section 1.7 in your study guide. The first inequality that I'm going to be dealing with is that of linear inequalities. The example that I've chosen is where there are simultaneous linear equations. So the question says solve, which as you know means find the value of the unknown or the variable, which in this inequality is x. So we have to solve the simultaneous inequality 2x plus 1 less than x minus 4 less than 3x plus 7. So the best method to approach solving such a simultaneous linear inequality is to start with the term that is sandwiched between the two outer terms. Right, now we see that there's a minus 4 there, so let's start off then by adding this minus 4 to the two outer terms. So we get 2x plus 1 plus 4 on the left side, and we get 3x plus 7 plus 4 on the right hand side. Alright, so now we have x less than 3x plus 11, and on this side we have 2x plus 5. Alright, now as you can see, you now have two inequalities to solve. This is why this is referred to as simultaneous, because you're going to solve the two inequalities simultaneously. Alright, so let's have a look at this inequality first. Remember, we are trying to solve for x. Right, so on this side we have x less than 3x plus 11. Okay, bring the 3x over. X subtract 3x is minus 2x, which is now strictly less than 11. One of the important properties of an inequality is that if we divide or multiply by a negative, the sign of the inequality changes. So if I'm going to divide the left-hand side by minus 2 and I have to divide the right-hand side by minus 2, the inequality sign changes and we get 11 divided by minus 2, which is negative 11 over 2. Alright, so that is on the right hand side. Now let's have a look at the other inequality, which is 2x plus 5 less than x. So this is a simultaneous linear inequality. Therefore, I have to get the solution that solves these two inequalities simultaneously. That means I use the word and. So it's 2x plus 5 less than x. 2x minus x is less than minus 5. That gives me x strictly less than minus 5. Right, so now you have a simultaneous solution. X has to be strictly less than minus 5 and x has to be greater than, what is this, negative 5.5. Alright, so how do we represent this solution simultaneously? So let us have a look at the number line to see what we have so far. On the number line, we now have x is strictly less than minus 5, okay? But at the same time, x has to be greater than negative 5.5. Alright, so let's have a look. Where is negative 5.5? It's over here. So it's strictly greater than. Open circles are for inequalities which do not include the endpoints. And there are your two solutions represented. X less than minus 5 and at the same time x greater than negative 5.5. if we are to represent this as a simultaneous solution, we are interested in these values, all right? So we're interested in the values from minus 5.5 to minus 5. Both of these endpoints are not included in this case, and that is my solution. So on the number line, the solution is represented as all the x's that lie between minus 5.5 and minus 5, but excluding the endpoints. If we write that solution as an inequality, we get the solution then to be negative 5.5 is strictly less than x, which is strictly less than negative 5. And this then is the simultaneous solution of the inequality that we started off with. All the x values where x is an element of the reals and x has to be greater than negative 5.5, so I use the strict inequality, and x has to be less than minus 5. So the solution then is the intersection of the two inequalities which we found by solving the simultaneous linear inequalities. All right. The next type of inequality is the quadratic inequality. Now, as you all know, quadratic comes from the terminology that we use when we're dealing with polynomials of degree 2. So let us solve the first quadratic inequality, which asks us to solve for x squared minus 4 is strictly less than 0. Now, with any quadratic equation, we are able to factorize it into its linear factors. And so in this example, the linear factors are x minus 2 multiplied by x plus 2, and we have to solve the product of those two linear factors strictly less than 0. All right, now if you look at these two factors over here, these two factors give us what is referred to as the roots of the quadratic. So the roots are x equals 2, x equals minus 2. If I sketch this solution for you, I will obviously have to sketch a parabola, because a parabola is the graph that corresponds to a quadratic x squared minus 4. So let us sketch this parabola and see what it looks like. Now I know that the roots or the zeros of this quadratic are positive 2 and negative 2. All right, so we've got our Cartesian plane with our x and y axis. We now know that the two roots are positive 2, 0, and negative 2, 0. If I sketch the parabola corresponding to the equation y equals x squared minus 4, I'm going to get a parabola which in this case turns on the y-axis. In fact, we know that it's going to have a y-intercept of negative 4 from the constant, and its axis of symmetry is the y-axis. All right, so now if you look at this parabola, we're now asked to solve x squared minus 4 less than 0. Now, strictly less than 0 in graphical terms means, where does the graph of y equals x squared minus 4 lie below the x-axis? Right, so let's have a look. Where does your graph lie strictly below the x-axis? Now remember, the less than 0 means that actually these two roots must not be included, and that is why I'm making them open circles. So negative 2 and positive 2 are not included for less than 0. I'm interested in that part of the graph which lies below the x-axis. All right, so can you see that this part of the graph here lies below the x-axis? So for which x values does the graph lie below the axis? Well, clearly it has to be from -2 to +2. All real numbers from -2 to +2, not including the endpoints. So that means that my solution is -2 less than x less than +2, x an element of the reals. If you can also write the solution set as x an element of -2, 2. So that will be the solution set for the inequality x squared -4 less than 0. Alright, now I've chosen the same quadratic, y equals x squared -4, which is this parabola here, and I'm asking you to solve for x if this trinomial or quadratic is greater than 0. Alright, so what are we interested in now? We're now interested in those values for x for which the graph, i.e. the parabola, lies above the x-axis. So now I'm interested in this part of the graph and that part of the graph. Those are now the parts of the graph for which the parabola lies above the x-axis. Remember, it's the same factors and therefore it's the same parabola. The zeros are still -2 and 2. The sign change of the inequality means you're looking for where the graph is positive. Okay, so this time I will have from +2, all the values to the right of +2 will be where the graph lies above the x-axis, and similarly all values to the left of -2 will be where the parabola lies above the x-axis. So I can write my solution now as x strictly less than -2. Now I must use the word or x greater than 2. We use the word or in this case because it's not a simultaneous solution. These two solutions are disjoint. There's no intersection between the two. That is why we use the word or. No x value can satisfy being smaller than -2 and being greater than 2 simultaneously. Alright, so if you want to write this in the interval, you can say x is an element of -∞, -2, union +2, +∞. The union sign is used for or, and then the intersection, as in the previous example, is for and. So that solves the two quadratic inequalities, and I've done it graphically. So this is one of the methods of solution that one can use to solve quadratic inequalities, is by actually using a graph to show your solution. Alright, now let us have a look at the inequality x squared plus x plus 1 strictly less than 0. Once again, I'm going to do this solution graphically. If you look at this quadratic, x squared plus x plus 1, you will see that we cannot factorize it into two brackets, because even if I try x plus 1 times x plus 1, the middle term would be 2x. So the middle term would not be x. Alright, so let's have a look at what would happen if we wanted to find the zeros or the solutions of the quadratic y equals x squared plus x plus 1. Let us use the quadratic formula to see if I can find the roots, because clearly we can't factorize this. Right, so there's my quadratic formula. In this case, my a is 1, my b is 1, the coefficient of x, and my constant is 1. Substituting this into the quadratic formula, we get -1 plus minus the square root of 1 squared is 1, a is 1, and c is 1, all over 2 times 1. Right, so now we get minus 1 plus minus the square root of 1 subtract 4, which is minus 3. Now remember, we are working with real solutions. The square root of negative 3 is a non-real number. If you try and work this out on your calculator, it will show maths error. So this has no real solution. Now, in terms of sketching this parabola, what is happening here with this parabola, if we have no real solution, is the following. Just to get a little bit more information about this parabola, I'm just going to work out its axis of symmetry so that I can get a bit of a turning point here. So I get minus 1 over 2 times 1. Right, so I know that my parabola is symmetrical about the x equals negative a half line. It has a positive shape because the coefficient of x squared is 1. So it's a positive. So if I sketch this parabola, what will I get? Okay, so there's my x-axis and my y-axis. It says that the axis of symmetry is negative a half. Right, so there's my axis of symmetry at negative a half. All right, so if you look at that parabola, what is happening now is that if you work out the turning point, i.e. you substitute negative a half into the quadratic, your turning point will be negative a half and the quadratic's value, the y coordinate, at negative a half. Now, it's not difficult to work out that y value because you simply substitute negative a half into the original equation and you get a quarter, subtract a half, plus 1. All right, so we get 1 minus 2 plus 4, and that gives me 3 quarters. Right, so my turning point is negative a half, 3 quarters. So this is an interesting graph because when you plot this graph, look what happens. So negative a half and 3 quarters, right? There's your turning point, negative a half, 3 quarters. The y-intercept, of course, is the constant, which is 1, so that's my y-intercept. So if I draw my parabola symmetrical about the axis of symmetry, x equals negative a half, I now see that my parabola lies entirely above the x-axis. So coming back to the question then, which asked, for which values of x is the quadratic x squared plus x plus 1 greater than 0, less than 0 for question 3, we see that this parabola will never lie below the x-axis. Right, so in other words, we can safely say that since this parabola is always above the x-axis, that the solution here is no solution. Right? In other words, there are no values for x for which this parabola will lie below the x-axis. So for the solution then, for the less than 0 inequality, there are no values for x satisfying this inequality. On the other hand, in question 4, I'm asking for which values of x is this quadratic greater than 0. Now, have a look at your parabola again. Can you see that this parabola always lies above the x-axis for all real values? Right, so then our solution here is x an element of the reals. This parabola, this quadratic, is strictly greater than 0 for all x an element of the reals. So there's your two opposites. One is no solution because it never lies below the x-axis, and the other one is for all real values, it always lies above the x-axis. And again, a graphical solution there showed the solutions very nicely. Let's move on to rational inequalities. So just to remind you, rational expressions are expressions which are the form P over Q, right? So they're fractions, where the numerator is an algebraic expression and the denominator is an algebraic expression. This time it's called a rational inequality because I've taken a rational expression, 2x over 1 minus x, and I'm going to solve this rational inequality less than or equal to 0. Now, what is important with a rational inequality is that we determine where this expression is equal to 0, and then we also determine where this expression is undefined. When you determine values of x for which a rational expression is equal to 0 or undefined, we speak about those values as the critical values. Alright, so let us write down the critical values, which I'm going to abbreviate as the CVs. So the critical values, right, let's first start off with, where is the numerator 2x equal to 0? Well, clearly 2x is equal to 0 when x is equal to 0. So that will be my one critical value. The other critical value is where is my rational expression undefined. Alright, so that would be where x is equal to 1. So therefore 0 and 1 are the critical values. Now, in order to solve a rational inequality, I'm going to show you the method where I use a number line and I create a table of signs across my number line. Right, so in the number line, on the number line, which represents all real numbers, I'm going to show my critical values first. Right, so x is equal to 0 is a critical value and x equals 1 is a critical value. We know that when x equals 0, my rational expression is equal to 0, so I can safely colour in the dot above it. And when x is equal to 1, the rational expression is undefined, so we leave it as an open circle because we know that division by 0 is meaningless. Now we are going to start testing values between our critical values to the left and to the right to ensure that we cover all real numbers. So let us start with any value for x less than 0. So you choose a value for x less than 0. For example, I will choose -1. I mean, this could be any value less than 0. Choose a value less than 0 and substitute it into your rational expression. If I choose x to be -1, I get 2 times -1, which is a -2, divided by 1 minus -1, which is 1 plus 1, so that's a positive. And a negative divided by a positive is a negative. So the overall sign for any x value less than 0 would be a negative. Similarly, choose a value between 0 and 1. So, for example, let's choose a half. If I substitute x equal to a half in here, 2 times a half, I get a plus. If I substitute x equal to a half in here, I get 1 minus a half, which is a positive, and a plus divided by a plus is a plus. Right, finally, we need to look at all values for x that are strictly greater than 1. For example, let's choose x equal to 2. Substituting x equal to 2 into the numerator, I get a positive. 1 subtract 2 is a negative, and a plus divided by a minus is a minus. Right, now this pattern of interchanging signs between the critical values is quite common when you're solving rational inequalities, especially the fact that there are no repeated roots or zeros here. Right, now the important thing from now on is to be able to interpret this number line in which I've indicated the signs. Let us go back to what we were originally asked. Less than or equal to 0. Right, so less than means negative, and equal to 0 is where we have a critical value that gives us the expression equal to 0. Right, so what am I interested in? I'm interested in all the negatives, and I'm interested in where the expression is equal to 0. I'm not allowed to include x equal to 1 because that would make the expression undefined. Right, so for strictly less than 0, it's the negatives, and for equal to 0. So how do I show what I've indicated here in red as my solution? All right, so my solution will be from x equal to 0 towards the left of the number line, towards the negative side, and then it says for the negatives, x can also be greater than 1. Please notice that I've included x equal to 0 because the inequality includes equal to 0, but I've excluded x equal to 1 because the expression would be meaningless or undefined if I included x equal to 1. So my solution for this rational inequality is expressed with these two red arrows. Right, so how do we write this? Well, this would be x strictly greater than 1, and this would be x less than and equal to 0. Right, so here's my solution then, x less than and equal to 0, and as you remember from the previous case, if there's no intersection between the two, I write or x greater than 1. And this will be the solution, x an element of reals, for this rational inequality. The next type of inequality I'd like to discuss is absolute value inequalities. Now you remember from our previous lesson on absolute values that the definition of an absolute value is that it is greater than or equal to 0 when a is positive, and when we have a less than 0, then we've got to do something about the expression between the absolute values. But for any a value, whether it's greater than or equal to 0 or whether it's less than 0, if you take the absolute value of it, you always have a positive quantity. All right, so in other words, what I'm saying is that this denominator here is positive. In fact, the numerator is also positive. So I have a positive over a positive, which means that this whole rational expression on the left-hand side is positive. The only critical value in this absolute value inequality is for where the denominator is 0. Okay, so let's have a look. Where is the absolute value equal to 0? Well, that will happen if and only if the denominator is equal to 0. That's the expression between the absolute values, which happens if and only if x is equal to half. Right, so x is equal to half is what is referred to as a restriction on this inequality. If you substitute x equal to half in the denominator, you will have 1 over 0, which is meaningless. So we'll have to keep that in mind when we write down our final solution. In this case, since the denominator is always positive, and we've excluded the case where it's equal to 0, I am allowed to multiply both sides of the inequality by the absolute value of 1 minus 2x. This will not change the sign of the inequality because the expression in the denominator is positive. And if I multiply an inequality by a positive quantity, it preserves the inequality sign. Right, so therefore I divide both sides by 3 and my inequality becomes a third is greater than the absolute value of 1 minus 2x. All right, if you prefer, we can write this as 1 minus 2x is less than a third, right? Which you're probably more familiar with. You remember that when I discussed absolute value inequalities, we said that the absolute value less than any constant is true if and only if the expression between the absolute values is sandwiched between negative k and positive k. So let's do the same over here. We're going to remove the absolute value sign and we're going to sandwich 1 minus 2x between negative a third and positive a third. All right, so this is an inequality that we need to solve. So in order to solve this inequality, what can we do? Well, certainly we can subtract 1 from both sides. So we get a third, subtract 1 on this side, and we get negative a third, subtract 1 on the left-hand side. So let's see what that gives us. That gives us negative 2x in the middle, a third, subtract 3 thirds, and on this side, negative a third, subtract 3 thirds, that gives me negative 4 thirds. Right, now you will notice that on both sides of the negative 2x we have negative signs. So let's change all of these to positive signs by multiplying the inequality throughout by negative 1. But, just a word of caution, if we're going to do that, if we're going to multiply everything by negative 1, then we've got to remember to change our inequality signs around. Okay, now we will have no problem in dividing our inequality by 2 because 2 is positive, and so if I divide this inequality by 2, remember division by 2 is the same as multiplication by a half. So if I multiply this by a half, then I've got to multiply this by a half. So my inequality becomes 2 divides into 4 twice, so it's 2 thirds is greater than x. 2 divided by 2 is 1, so it's a third. All right, so do you see our solution now? Our solution is a third, strictly less than x, strictly less than 2 thirds. However, what do we have to remember? We said that our denominator may not be 0. All right, so we have to exclude a half in our solution. So if you represent the solution on the number line, you will have a third, a half, 2 thirds, and 1. So we want a third, strictly less than x, strictly less than 2 thirds, but at the same time we do not want x to be a half. And so there is my solution. Starting at a third, ending at 2 thirds, excluding the endpoints and excluding a half. To end off, I would like us to think about this inequality. 1 plus x over 1 minus x greater than or equal to 1. So this is a rational inequality. Right. Now, a typical error that is made by many students is this concept of, oh, I'll just multiply both sides by the denominator, which is something that one does when you have x over y equals a over b, and then I do this process of cross multiplication and I get x times a equals y, x times b equals y times a, right? So that's the principle of cross multiplication. Now, cross multiplication may not be applied to inequalities, right? Let's investigate why this is incorrect. First of all, we have no idea what the x value in the denominator is. So what happens if x is equal to 1? Well, we have a problem then, because then I'm dividing by 0. All right? So if division by 0 is meaningless, cross multiplication is also meaningless. So this process of just simply multiplying both sides by 1 minus x is not allowed with inequalities, because we're not sure what the value of the denominator is. So x equal to 1 is a problem. The second problem we have is what happens if 1 minus x is less than 0? That is also a problem. Not because it's now division by 0, but because if this denominator is negative, what would happen if I multiplied both sides of this inequality by a negative? Then we know that there should be a sign change. The inequality sign changes when you multiply or divide by an inequality. So therefore, please be careful when you have rational inequalities to do the process of cross multiplication. So I would like you to try this very example. It is in additional exercise 1.7.1 in your study guide, page 17. I would like you to try this example. Please do not follow the route of cross multiplication, but rather follow the route that I showed you in the previous example, where you have to set your expression on the right hand side so that there is a 0 on the right hand side, and then you proceed with a lowest common denominator of 1 minus x, where x may not be 1, and then you will have a simplification which will give you a rational expression greater than or equal to 0, and then you can proceed with the number line and the alternating plus minus signs as I showed you in the previous example. Good luck with your inequalities, and let me know if you are having any more problems with them.